Okay. So where is the normal vector? The normal vector will be this one. You draw the vector that's perpendicular to the surface. Okay. What is the angle made of the electric field vector and the normal vector theta? Can you get that?
60.
60 degree,
Yes.
30 degree, 60, right? 60 degree. So I have to correct that here. 60 degree. Cosine of 60 degree is 0.5. Right? Then substitute the EA cosine here. What do you get? You have to calculate the area. The area now is one side is 30 centimeter, right? Multiply with the side here. What is the side here?
10 căn 3 này.
10 căn 3 không? Chắc chắn là
Không
10
phải. Em nhầm.
20 chứ đúng không? 20.
Trên ti 20.
20, right? Please pay attention for that. So in this case, you have the area of 30 times 20 centimeters square, right? So you get the same answer as question A. Is it interesting? You see why? The reason why. Yeah. Let's come back to the angle theta. The angle theta made of the yellow vector and the E vector. So it must be this angle. This angle. Oh, sorry. No. This angle. Can you see that? It's a little bit difficult to measure this angle, right? So if you look at the box from the side, you look from this side, you can see that you have the triangle here. Right, when you look at from the side here into the box, you have the triangle here. You have the normal vector here. This is the perpendicular to the slanted surface, right? The electric field is this. electric field is this vector. I draw it in red. Right? So the angle made of this and this will be exactly this angle, right? This angle. It is. The same. So you get 60 here and 60 here. Okay. Now for the question C. For the question C. Can you still hear me?
Yes.
So now for the question C. The entire box. So you have the green surface, you have the purple surface here, and you have another three surface, right? One is this surface, another one is this surface, and then at the bottom, right? But you can easily see that the flux through these three surfaces are zero because the electric field is perpendicular to on the three surface, right? The two on the two side, front side and back side here and the bottom. So the sum of all surfaces here can be something, right? Oh, I still have the drawing. Okay, but if you want to calculate the entire surface box, you have a so-called closed surface, right? Then in this case, you have to choose the normal vectors. The normal vector must be out or must point out from the box or the surface. So you have to reverse the normal vector of the green surface into the opposite direction, right? So you cannot take this vector anymore because this is the closed surface. This is the rule. New rule. So you have to remember that. Okay. So if you do that, you have to reverse the normal vector of the green surface. So I have to calculate it again, but in the opposite direction. So I have here the angle of 2 pi, pi, sorry. And then here you have -1 instead of 1. Then the surface, the green surface now will have the flux of minus 2030, 340. Right? Because now the normal vector is the opposite direction. Then you have the purple surface with this one. This is for the vertical. This is for the slanted. Then you can easily get the electric flux total will be 0. Okay. And this is the part of the Gauss law later. When in the closed surface, you do not have any charge. Yeah. We don't have any charge inside the surface here. Then the flux of the electric field through this surface, this closed surface, will be 0. This is one point of the laws. Okay, any question? When you don't have any question, we can go a step further. Remember back, still now we have the uniform electric field and the area is flat. But now what happened if the electric field isn't uniform and the area must not be flat? What happened? So I copy this one down to the new slide, and you can see the new condition, right? We have electric field is non-uniform, right? So E isn't constant. The area must not be. It can be flat or it can be not, right? So in this case, you have to use the integral technique again, right? So you have to use the integral. And this is exactly what you need to use. You have to divide the surface into many small pieces and take the dA vector, the differential area, like in this figure. Yeah, you have the surface here. It can be floods can be flat, cannot be flat, no problem. Take the delta A or smaller dA, then you calculate the angular theta I here. And EI is the electric field at this point. At another point, it can be different. For example, here, if I draw the E vector at this position, it may be this. Right, so you can see that the electric field isn't uniform, or we have the non-uniform electric field. Okay, E at this position is this, at that position it may be this, right? So E electric field isn't uniform anymore. Okay, so I will show you how we calculate this by solving this example. Nên ngồi trên này cho nó gần. So first of all, you have to identify the surface, right? According to the problem here, the surface can be this. Okay. It is in the X, Y. So this is the y axis. This is the x axis. So it's in the xy. Alo, nghe chưa anh? Ừ. Rồi để mình quay lại. Còn mày em vậy. Mà muốn gì vậy? Muốn gì? Rồi biết, nhưng mà vì từ sáu rồi mình lại đi ra mình đọc đi, ok rồi tại vì mình quay lại mình để cho nha. Rồi. Nhưng mà nó học, nó học đến 3 tuần rồi lớp vô kịp không, bạn ở bằng vô có kịp không? Nó đầu tiên thứ sáu Tết 2 tuần rồi em quên rồi. Nên ờ, 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 rồi, nam hay nữ vậy? Ok, rồi để xem. Yeah, you see, we have the XY coordinate system like that. I have to copy the text box. This is the X axis. This is the Y axis. Okay, the origin always here. Okay, we have the surface. Where is E? Where is E? E vector can be somehow here because we don't have A, B, and C here, right? So we just draw the vector like this. If we have the exact value of A, B, and C, you can have the correct E vector. Now we apply the definition here. We calculate the, sorry, what happened? Right, we take the E vector and dA. Now the problem is dA. For dA, we should take the very small area, right? Very small area in this. I mark it in yellow or white. What happened here? Yeah, I take the small area here. I call it dA. So where is the dA vector? The normal vector of this one, I can take the normal vector, yellow vector here. Can I put it this way? Yes or no? The normal vector of the dA, the small yellow piece. Yes or no? No, because the area is in the XY plane. So the normal vector here must be perpendicular to that, right? So it must be parallel to the Z axis. Is this? Is it clear? So I have to take the normal vector upwards like that. So I will have the dA vector like, I copy this one. dA vector is K. Do you agree with me? dA for this case is K. But multiply with the area dA. So dA, I write dA K. Okay? Copy here down. Do you agree with me? If yes, then type the number 1 in the chat box for the dA vector. Number 1, please. When not, then tell me why. Hello. Are you still there?
Yes.
Yeah, do you understand that? The dA vector equal to dA times K. dA is the area, the yellow area here. And K is the unit vector of the z-axis. Okay?
Yeah.
But another people, hello. Do you agree with me? Type number one, please. Yes, I see here some. Okay, thank you. Then let's calculate EDA. We do that step by step. What is EDA? E dot DA will be what? E dot DA. Oh, big dot. E dot DA will be E dot DAK, because DA vector is DAK. Then you substitute the E given by in the example into that, you get E is AY I plus BG J plus CXK CSK, right? So you have to calculate the dot production of the two vectors E and dA. But E have the components EZ, EX, EY is given in the formula. Yeah. Gì vậy? À, để lâu gọi là tương tác hả? Okay. Then for the dot production here, you have I dot K, oh, not I, J, sorry. For the second vector, I have to have J. J dot K is 0, right? So you get only K dot K is non-zero. So the dot production of the two vector here is CX only. CX only. Now, for taking the integral, you have to identify the range of the area here. It's given here x from 0 to w. So you have here w, y is from 0 to h. So you have here h, right? Italic, CXK, yeah. DA, sorry. You are right. DA. CXDA. Yeah. Okay. The DA is the differential area here is dx, dy. If you have this in the mathematics. So dA equal to dx multiplied with dy. This is dA value. Right? Because it is in the Cartesian coordinate system. Then you substitute that here. You have Cx dx dy. Add the dot here to the equation. Then you have the integral of that. The integral of this equal to the integral of that. Right? But you have to have here the multiple integral. Triple. And the range of the x integral is from 0 to w. For the y is from 0 to h. So you can get the interval like this one. Okay. C is constant to put it out. Then you have the integral from 0 to w of x dx and multiply with the integral from 0 to h of dy. And finally, what do you get? You get c over 2 w square h. nhé. Thì tích phân mình học ổn không? Tích phân cơ bản thôi, không phải là tích phân cao siêu gì. Ok, nếu mà mọi người hiểu được luôn cái chỗ này thì gõ số 2 vô giùm thầy cái. Gõ số 2 vô cái chat nha. Rồi, cảm ơn mọi người. Dễ hay khó? Ok, bây giờ mình nghỉ giải lao tí đi ha, giải lao 10 phút đi rồi vào lại. Ừ. Ừ. Lúc sáng nay phải không? Ừ. 2 bữa vừa rồi em không có đi học nhưng mà không tham gia. Nhưng là bữa bệnh rất là nhiều học nên là em đi đăng ký một. Ừ. Thành ra thì buổi đầu cũng có. Là có. Okay, please come back to the class. You see that the area here given in this problem is flat, right? But the electric field isn't uniform, so you have to calculate the integral. Now let's say we would like to calculate the electric flux through a closed surface, but in which we have the very special surface. Let's say the sphere, the cylindrical, and so on. Okay, so now let's imagine I have a point charge here. Okay, and if I draw the sphere surrounding the charge, what do I get? So you can see that if I draw the sphere surrounding the charge here, right? Then in the plane of the screen here, or the board here, I draw the charge, a small charge here, positive. So I draw it in red. Okay, and I would like to calculate the flux created by this charge through the sphere here. So I have the case in which we have a charge. Then we want to calculate the electric flux through the sphere. The electric field is created by a single charge. Okay, this is the case we have here. Let's say we have the sphere here with the center O and the radius R. The radius of the sphere is R here. So in this case, you have electric field at a point on the sphere. Let's say this one will be this, right? And another place, it will be this. Oh no. Can you see my screen now?
Yes.
Okay. At another place, it may be this. Right? But everywhere it's the perpendicular to the surface, right? Because the field here is radial. It points from the positive charge in the center outside of the sphere. Then first of all, we need to calculate this, right? You see, we have only field equation for that. But now let's say if I take the area, a small area here, I take a very small area here, right? Then this is dA. This is dA. So how is my differential area dA now? Is it dAk anymore? Right? I don't know where k is, right? Because we don't know x, y, and something here. So that in general we say dA. But I can draw the dA vector, right? dA vector is a vector that is perpendicular to the dA here. So I draw a little bit, big dA so that you can see it clearly. Okay, this is my dA vector. What's the E vector at this position? Right? E vector. If I draw the vector at this position, it must point out of the surface, right? So in this case, dA is parallel to E vector, right? So you have the cosine theta is 1. And remember vector outwards of the sphere. So the yellow vector is correct already. So they are parallel with each other. So E and dA. I mark it for you. E and dA. This is the dA vector, the yellow. But I don't have K anymore. Right? And what's the E vector? Okay, now at this area dA, we have the differential. I copy it from the previous. Then I have the differential flux, EDA. So I can call it d phi. If we want to do, is E dot dA, right? No K anymore. But it is equal to E dot dA. Why? Because we don't have any cosine more. The cosine is 1. Okay, so you see from the previous E vector dot dA vector, you get the production of EDA only. This is numerical value, EDA. But what is E? Now, the electric field at this point is E equal to KE Q. Let's say the charge of the particle is Q divided by R squared, right? Where did you have that? In the previous chapter, okay? Electric field created by a single charge at the distance R. So you have d phi is EDA, but E is. So if we want to calculate the total flux now must be the integral, right? Phi equal to the integral. Then you can see that the E can be put out of the integral. You have the dA only inside the integral. Right? Because E is constant. E is constant. Right? It means we have to calculate the area of the surface here. The surface is the sphere with the radius R. So what do you get? What do you get here? I substitute the E. E is KE Q over R squared. The dA is 4 pi my computer doesn't work anymore. No. Again, I substitute the value of E KEQ over R squared multiplied with 4 pi R squared. If you remember, then the KE can be written by 1 over 4 pi epsilon 0, right? KE, another way to this to calculate KE. KE is 1 over 4 pi epsilon 0, right? With the value of K like this, then you get phi. What do you get phi? Now, as the total flux. Is it equal to Q over epsilon 0. This is a very important result. What can we conclude from this yellow result? The results doesn't depend on the radius r. This can be big, can be small, right? Can be very big, can be very small. But the flux through this sphere is constant, right? It depends only on the charge q of the charge point, and the constant epsilon zero, of course. But it depends only on q, right? So it means you can draw the bigger sphere, smaller sphere, and so on. And even if you draw the surface like this, the surface of any shape like this, right? The red surface here. Then you can see that, or the green, I think it's the green, right? Then if you calculate that, the flux through the green surface, now this isn't the sphere anymore, right? It still be equal to the q over epsilon zero. So this is the Gauss law. The Gauss law states that if you calculate the electric flux through the closed surface, it will be equal to the sum of all the charges inside the surface divided by epsilon zero. Right? This is, in general, you can take the Q inside. In here stands for inside. Right? It's a very important law in electricity. Let's come back to the previous example here. What is the flux through the box? We calculated that, right? And the answer is 0. Is this? In the vec shape box like this, we have the 0 flux, right? Why? According to Gauss, there is no charge in the box, right? Then the flux is 0. Now imagine that if you relocate the box inside this electric field, let's say we rotate the box somehow, right? We rotate the box, we flip the box, right? We do something with the box. We can resize the box too, right? Reshape the box too. In this case, because inside the box we don't have any charge, then the flux through the charge the box, sorry, is 0. Is it important? Yes, of course, right? Then we have the Gauss law. I copied the Gauss law from the book so that you can read. Okay. So this is what I have from the book. Okay. The integral of EDA, so the flux will be equal to Q in. This is the Gauss law. Regardless the shape of the surface. Then we can apply the Gauss law to answer some question or solve problem. This is the first example. Let's rank the electric fluxes through each Gaussian surface. Gaussian surface is the surface we use to apply the Gauss law, right? We call it Gaussian surface. So we have some sphere, we have the box, we have the cylinder, and the electric charge for the A, B, and C case is inside the box. Just for the D is outside. So let's rank the electric fluxes through the from largest to smallest. And if there is some equality, then mark that. Right? So you can apply directly the law. For the A, it is for the A, you have Q over epsilon 0. For the B, you have Q over epsilon 0 too. You have only one Q inside, right? For the C case, you have 3Q. For the D, you have 4Q. No, we have 0 Q inside. Yeah, 4Q is outside of the sphere. So you have 0. So from these reasons, you can range from the largest. So largest is C. A and B are the same. Right? I will send the presentation later into the Zalo group. Okay, then the total and the smallest is D, right? The smallest case is D. But if you just apply the Gauss law for that, this is nonsense, right? Because Gauss law is a very big law, but you apply that in just like the game like that, then this is just an example for that. Gauss law can be applied to calculate the electric field in some special cases. Remember back to the previous chapter. If you want to calculate the electric field, you have to apply the integral, right? If you have the shape, an object of any shape, then it's not easy at all. But if you apply the Gauss law for that, it will be easy for you. Okay. So let's go a step further now. we will apply the Gauss law. Sorry, Gauss law to calculate electric field. Okay. The first example is for the sphere. Now I have a solid sphere, this one, with the radius A. And the total charge is Q. Then I would like to calculate or identify the electric field outside of the sphere and inside of the sphere. Right? For the point here and for the point here. If you apply the integral technique, okay, please, if you can, right? But whenever we know the Gauss law, we don't calculate the integral anymore because Gauss help us to do that easily, very, very easy. Okay, so let's start with the situation in which we have the charged surface, the charged object, the solid sphere with the total charge Q, right, like this one. The only condition in which we can use the Gauss law is we have to have the symmetric configuration, right? So I write here the note. Here, just line symmetric configuration. If you have the non-symmetric configuration, then please don't use the Gauss law. Okay, so now let's start with that. Imagine that the sphere here is uniformly distributed charge. It means the charge density of the sphere everywhere is the same. Okay, so let's say at this point, the flux through this sphere is what? We can apply directly the Gauss law in this case, right? The flux is Q in over epsilon 0. And we know that there is only someone write something here. Okay. The flux is Q over epsilon 0, but we have here the capital Q, so I write in capital Q. Right? We know it. But in this case, if we draw the surface at the point we want to calculate the electric field at this point is what we want to have, right? But we know that the electric field at this point because of the symmetric configuration must be this vector, the right vector. We don't have any other direction for E because the sphere is symmetric, right? Uniformly distributed charge. Then E at this position will be that. If you agree with me, then type the number 3 into the chat box. The E vector at this position is radial, like this. It's easy if we have the point, right? But now we have the sphere, but we still have the electric field like this. Okay? Number 3, please. No 3. Okay, thank you, Nhật Minh. Oh, you give me number 5 or what? What do you mean H, Hoàng Nam? Okay, now, what is the flux from the calculation, right? The total flux must be this. The total flux must be phi total equal to EDA, but you can see that because you have the same distance for every point on the Gaussian sphere here, right? The Gaussian sphere is the sphere that we draw so that the sphere consists of the point we want to calculate, right? We don't draw another sphere. We draw the sphere that exactly consists of the point, right? Or in other way, the point we want to calculate electric field must be on the surface we draw. Okay. Then we want to know E. We don't know E now, so E must be E. The area is 2 pi over r, the 4 pi r square, right? Because the area here, but I have to use the small r, not the capital R here, right? Small r for that. Give me some second to plug my computer in. After the long holidays, so everything is chaos. Okay. So we have the first equation here. Number 1, the yellow one. The equation number 2 here. Number 1. The equation number 2 here. Can you find out the electric field E at the point at A here? And not only at the point A, at any point on the surface will be from the equation 1 and 2. What do you get? You get E equal to K Q over 4 pi epsilon 0 and r square, right? Right? But remember, you can substitute the 1 over 4 pi epsilon 0 with ke again. Then a step further will be this. Ke over r square, like this. The green one. What can we notice here? What can we say about the results? Is this familiar to you, the formula? The electric field here is exactly the same as if we have the single charge at the center of the sphere. It is? It's exactly what we had before. Here, if you have a single charge, then the electric field is KEQ over R square. It is? Now you have the sphere. It isn't the point charge anymore. It's big, right? But you have the same electric field formula. So as if we have the charge at the center, right? And remember back to the problem you solved before. If the object is far away from the charge, you can assume that you have the single particle, right? The charge particle. So this is the case outside the sphere. Okay. Now what happened inside the sphere? Here, somewhere inside the sphere. So now I copy the picture here to another case. Now I have outside the sphere. Outside. Inside, sorry. So I have to add the case outside the sphere here. E field outside. Then now I would like to have the E field inside the sphere. So I do have the same Gauss law, right? Because Gauss law is unchanged. Gauss law stated that we calculate the Q in, right? But let's say I want to calculate the electric field at this point. So set back. Now I want to calculate the electric field at the point inside the sphere. Let's call the point B. But do you agree with me that the electric field at the point B is radial again? Yes, because of the symmetry of the system, of the configuration, right? Symmetry. It can be different, right? It can be other direction. E must have this direction only. Okay, so now I apply the Gauss law. The Gauss law say that right. But now what is Q? Q in. Right? This is not Q anymore. It must be Q in as the original written. Q in. Right? The problem now is bị lại. Now you have to calculate the Q in. Q in is the charge inside our Gaussian surface or Gaussian sphere now. So the problem now is calculating Q in. Q in is equal to the density rho of the charge multiplied with the volume. Yeah. Này nó cẩn thận nó không cho mình ủa sao nó có bị cái này ta. Rồi cái gì nó cứ đưa kịp mình. Ok. Cũng con nữa. Okay, so let's calculate Q in. Q in is rho V. Rho is the density, charge density, V the volume. So you can calculate rho. Rho is Q, the total charge, divided by the volume of the big sphere. This is 4 over 3 pi r triple. The V of the small sphere will be 4 over 3 pi square small r triple. You get that? Cái này làm sao thoát đi nhỉ? Okay. So Q in is this. You can see that we can cancel the term 4 pi over 3, 4 pi over 3. So that you have the simpler. Okay, so now it's Q in. When you substitute Q in into phi total, you get the phi total. Okay. But now, what is the total flux when we want to calculate that by the definition? So you again you get flux, total flux is equal to the integral EdA. E is the same everywhere through this small surface. You get E out of the integral, you get E, and the integral of dA is the sphere area. So 4 pi r square, you have that. Then here the electric field at any point on the sphere, let's say inside, right? You divide the flux by that one, what do you get here? To divide the flux by 4 pi r square, you get here, but you have the fraction of r triple over r capital R triple, like this. Right? Again, you get the KE, but now you can cancel 1R from here to R square here. Finally, you get KE in the numerator. And you get here R square, R triple, sorry. Like this. So here is the inside, so I have to add the inside subscript inside here. And of course, for the previous one, I have to add the outside. No, and here. Okay, let's do it later. Then you see if we draw a graph for the magnitude of the electric field from inside to outside of the charged sphere, you can get this graph. See that? Inside the sphere from you, when you go from the center of the sphere out, then you have the linear function of that, right? You have here linear function. But from the outside, from the edge of the sphere out, you have this one. But I have to use the A, right? Because A is the radius here, so I have to substitute the R, capital R with A. Capital R with A. Capital R here with A. So you get the same formula as in the book. Right? You had A. So you see, if we calculate it directly from the integral, it's very difficult, right? You have the triple integral and so on. Now let's take another case. We have the very long straight line that is uniformly distributed of the charge. This one. In this case, the line is very long and the density, charge density is constant. And we have lambda for that, right here, per unit length, lambda, right? So if we look down from one end of the lines here, you can see that we have the uh, point line at the center, and the electric field is radial again. It means everywhere outside of the line here, the electric field is perpendicular to the lines. Why? Because the line is very long. So at any point on the line, we can assume that this is the midpoint of the line. It is because the line is very long, right? So any point on the line can be the midpoint of the line. Then we have the symmetry in this configuration, and E must be perpendicular to the line. Okay. Now imagine that we have to draw the closed surface so that we can apply the Gauss law. The Gauss surface now is this one. This is the cylinder with the two cap on the bottom, top and on the bottom, right? So you have the cylinder surrounding the line with the radius R in the figure, and you have two caps, top and bottom cap, right? And you see that in this case, at the top and bottom, E is parallel to the surface. So the flux on the top and on the bottom surface will be zero. Okay, zero. And for the flux here, you can see that I can easily calculate the flux like here. The flux through the side. When you cut the side out, then this is real rectangle. Okay, this is the curved surface, right? But this is the flux total will be the side only because the top and the bottom is zero. So you have E dA, but E have the same value everywhere. So we can take it out. And here you have EDA, but DA now will be the side here with the length L and the circumference 2 pi r. So you have here L multiply with, where is L here? The length L multiply with the 2 pi r. Right? 2 pi r. Okay. Then from the first equation here, you see what is Q in. So I copy this one to the new slide. What is Q in now? Can you identify Q inside the box? So you can see that only the segment, only this segment from this point to this point, right? Is inside the box, right? From the center of the circle here and center of the circle on the bottom will be inside. So it have the same length as the side, right? As the height of the cylinder, same length. So Q in now is Q in now is just lambda multiplied with the length L. Right? This is for the equation 1. Right? Then for the Gauss law, you have flux just some minutes. Flux is equal to Q in over epsilon 0, right? Equal to the equation number 3. Then from the equation number 1, 2, and 3, you can easily get the E. What is E now? E is equal to Q in over epsilon 0. Q in is lambda L. Right? Epsilon is 0 is epsilon 0. The area is 1 over L 2 pi R. This one. But you can simplify it a little bit to get the clearer. You have here lambda over 2 pi epsilon 0 R. Okay, so finally you have this one. Okay, so we have to end the class now because some people come here. I will send you. Yeah. Công thức của nó bị chạy cái. Next week we have the offline class, right? So please come and I will send the presentation file today to the Zello group for you. Okay, thank you for your attention. Have a good day.